Okay, so good morning. So over the last two lectures, we just go over a binary search tree, and in binary search tree we learned 7 operations, and so which are listed over here. And so first we learned the traverse function. So with the help of the traverse function, we're able to go through every node in the binary search tree and print out the values of them. So we learned 3 different orders for that, which are in order, pre-order, and post-order. And what we learned is that the in order is going to help us to print out the values from the smallest to the largest in ascending order. And the complexity of traverse function is O(n), because giving a tree with n nodes, we need to visit every node at least once. That is how we get the O(n) complexity. And so and after that, we learned 6 more functions. The most important one is here is search. And so with the help of the binary search tree property, let's say if we want to search for value, if the root node is 15 and then we want to search for the value 12, so just standing at the root, we are sure that we can totally ignore the right subtree, because all these values in the left, all the values in the right subtree of the root node is going to be larger than the root node, and so as to larger than our target, so which is out of our interest. So then we only need to go left. So basically, with the help with the binary search tree property, when we are performing search on each level, we just need to visit a single node. So it's like when we reach a node, we actually have 2 ways to go, either to go left or to go right. But with the help of the binary search tree property, we only need to pick one of them to visit. So and with this property, we are able to get the OH search complexity, where H is the height of the tree. And then we learned 2 more functions, which are minimum and maximum. With them, we are able to find which we basically go to find the leftmost or the rightmost node in order to find the minimum and maximum value of the tree. And then we learned a successor function. So the definition of successor is basically another node in the tree which holds the smallest value that is larger than the node that we're currently looking at. So, and also it is OH complexity, because we only need to go down, either go down from the target node X or go up. So we can only either go down or go up by each levels. So, and then we learned the insertion and deletion. Both of them also have the OH complexity. So from here, you can see that all these 6 functions have the OH complexity, which means that so the efficiency or the performance over a binary search tree heavily depends on H, the height of the tree. And so previously, have we discussed what? Do you still remember what is the relationship between H and N?
Isn't it the height of the tree?
Yes. So what is the relationship between the height of the tree and the number of nodes in the tree?
The more nodes in the tree, like the greater the height.
In general, yes, more nodes meaning higher height. Yes, that's true. But do you still remember the mathematical formula I give to you? So, okay, let's look at this example first. So let's say, are both of them binary search tree?
Yeah, they're both right.
Yes, both of them are binary search trees. And do they store the same nodes or the same values? Do these two binary search trees store the same values?
Yes, they do.
Yes. But say here, what we can say is that here we got two binary search trees with the same nodes, basically with the same values stored. And so what is the height of the left tree?
3.
3. And what is the height of the right tree?
5.
5. So which one is better?
The one on the left.
Yes, the one on the left, because its height is lower, and which means that when we are performing either search or insertion, or minimum and maximum, so it is going to be faster on this tree, right? So with this example, what I want to show is that even though we are giving a couple of trees which store the same nodes or same nodes, so they can have very different height. So the height of the tree is this. Okay, so the height of the tree is this. H is larger than or equal to log. Okay, so the relationship between the height of the tree is this. H is larger than or equal to log base 2n, whereas less than or equal to n, where n is the number of nodes. So when the tree is this way, is in this way, balanced, meaning that on the left hand side and on the right hand side we have similar amount of nodes. So we call this balanced. When the tree is more balanced, so we are close to this value, log n. So the tree head is going to be very close to log n. So whereas when the tree is unbalanced, we are going to be on this side. So we are going to have a height which is more close to the number of nodes in the tree. So this is unbalanced. You can see over here on the left, in the left, we basically have no node in the left subtree of the root node, whereas we got quite a few nodes on its right subtree. Okay, so basically we want to have a tree which is pretty much like this way. So it is more balanced. Say so this is a more balanced tree. This is a more balanced tree, and then an extreme case is over here. Say if we have a tree like this, then the height of the tree is going to be, we say this is unbalanced. So if we have such an unbalanced tree, like which is as unbalanced as this one, so we're going to have h equal to n. Okay, got it? And question with this?
Understood.
Okay, so in order to get a better performance from a binary search tree, we want the tree to be as balanced as possible, right? So that given the same amount of nodes, the height is going to be relatively low. Mm-hmm.
Professor,
Say it.
I was wondering, based on how I looked at the homework program, and how are we supposed to, I guess, visualize the tree by program?
Okay. So the question is that how are you going to visualize the trees? It's very difficult for you to visualize that. So because I mean, by visualizing, I think most of you would expect to say something like this, right? Which is pretty cool. And in Java, this is very difficult for you to do because you need to, when you are printing out these values, you need to know which level are you on, and then put a certain amount of index on a specific level. So, and that's really difficult for you to do. But I think a relatively easier way for you to do the visualization is this. You just call the traverse function. For example, just call the in order traverse function over the tree, so that when you are printing, so when you are doing the in order tree traverse, basically you are going to print out all the values from the smallest to the largest, so that this can give you a sense of, okay, what kind of values have you already stored in this tree. Make sense?
Yeah, like would I don't know if you explained it before, like, but would we have to find like the height of the tree?
I mean, oh, so could you please repeat your question?
Yeah, like how would we know what the height of the tree is?
What is the height of the tree? Okay. There's so if you want to know, given a tree, if you want to know the height of it, so you need to design a very, you need to write a function. Okay, so basically the function is this way. It will try every route from, so it will go through the every route from the root node to every leaf node, and find, okay, what is the maximum length of each route, and that would be the height of the tree. And again, that is not easy. So you don't need to worry about the height, because so when you're doing your homework, there is nothing that is strictly, so you will not need the height.
Okay, so we just like do our best to implement like the functions you told us, and now worry about.
Yes.
Okay, thank you.
No problem. Okay, so yes, so this is the so any other question for me? Okay, so if no more questions, then I'm going to continue over here. So the point is that so basically we want to utilize every space in a tree and then make it more balanced, so that we can reduce the height of the tree. And so this is the point of binary search tree. And that so then people design a more advanced version of the binary search tree, which guarantees that the height is low. So if we only have a binary search tree, what we can tell is that, okay, in the best case, we'll have log n hat, whereas in the worst case, we're going to have a n hat. Okay, we will have the hat is going to be large as n. And then people design a more advanced version of binary search tree called red-black tree. And the red-black tree is going to guarantee that the height of the tree is this, is as low as log n, but as high as 2 log n plus 1. And this value is going to be much lower than ON. So over here you can see that in the worst case, the red-black tree is going to have a very good height, a very low height compared with binary search tree. This is the upper bound of the height given by binary search tree, whereas this is the upper bound of the red-black tree giving of the height given by red-black tree. And this is the advantage of red-black tree. So in the worst case, it guarantees that you can get a very good performance. Okay, so and the design of red-black tree is really cool, and it's really difficult for us to understand it. So let me put it in this way. In terms of search, if we worry about the search speed, so let's say so far we have learned something like array, linked list. Okay, And these are the two data structures that support two of the most basic data structures that support search. And what is the search complexity of these two data structures? What is the search complexity of these two data structures?
Is an array O of n?
Yes, both of them have
Both of them.
O(n) complexity. So in the worst case, we have to go through every value or every node in the linked list to find a target. And then, so we learn something like binary search tree. So the search complexity of binary search tree is this. In most cases, okay, so let me say, it is like anywhere between log n to n. So it is in this range, okay? So this is the search complexity over binary search tree. And then, so the search complexity of red-black tree. I'm going to use RBTree to denote that. It's going to be, its lower bound is log n, whereas its upper bound is 2 log n plus 1. And with this we can say it gives us log n search complexity. Okay, so then if we want to use a different example to understand them, okay, so you can take array and linked list as something like Toyota or Honda. Nothing fancy, but they're easy to maintain. With an array, it's pretty easy for us to maintain. So we just we can easily change the value, change its value, and to insert something into an array is not going to be too difficult for us to write a program to do that. And so they're pretty much like Toyota, Honda. So you just need to change the oils and change the tires, and then yes, it runs, but it's not fast. Then the binary search tree, I would say it's pretty much like maybe something like a BMW, and so it's fancier. It's definitely fancier, so that it's faster. So in most cases, it's going to be faster than Toyota or Honda. But so if you want to do some insertion, if you want to insert a new value into the binary search tree, then it will take quite some efforts because you have to deal with it in a very intricate way. So and then RBTree, I would say RBTree is probably something like a Porsche or even a Ferrari. So something like that. So they're extremely fancy, and which means that to build them, it's going to the design of them is going to be the design of it is really complicated, and also it's hard to maintain that. But we can get a very good performance from that. So let's just use Ferrari as an example, okay? So which means that sorry, let's just use Porsche for RBTree, and so it's guaranteed to be fast, but it's very costly for us to maintain. So with that being said, I'm not going to say introduce the details of RBTree. Instead, I'm just going to give you a brief view about it. So the reason is that this is just for knowledge, and in your job interviews or in your future work, no one is going to expect you to implement a RBTree. So no one expects you. So then you just need to know that there exists such a data structure which guarantees O log n complexity, the O log n height in a tree. So the RBTree is basically a binary search tree. It's basically a binary tree that satisfies the following properties. First, every node is either black or red. So that's why we give it the name red-black tree. And then its root must be black. And every leaf node, including the new node, is also black. And if a node is black, then both of its children, if a node is red, then both of its children will be black. And then for each node, all the simple paths, meaning that all the paths from the node to its descendant leaves contain the same number of black nodes. So this is one example. So of a red-black tree. So what we can observe is from this example is that the height of the tree, the tree is pretty much balanced. It's very balanced. We don't have an extreme case where we got something like this. No, so it's guaranteed that we are not going to get an extremely unbalanced red-black tree. It cannot happen with these properties. We will definitely not have something like this, have a tree structure like this. Instead, the layout of a red-black tree is guaranteed to be balanced. So that's why so with n nodes over here with n internal nodes, the height is at most this 2 log n plus 1. So this is what we discussed previously. And so this is the design of red-black tree. You just need to know that there exists such a data structure, which is better than, you can take it as an advanced version of the binary search tree, but it is out of the scope for you. And then there is another data structure, another two data structure that is widely used for search. And so one of them is basically an extension from a red-black tree. So it is even more advanced than red-black tree. We call it B tree. Or B, here the B stands for balanced tree. So B stands for balanced tree. And then the height of the tree is also this, O log n. But so in general, its height is even lower than RBTree. So it is more advanced. And so in you're only going to have a touch with this data structure in your operating system class, or in your database class. So you can take this one as something like, I don't know, giving me a car brand that is let's call it Ferrari. Okay, let's just say Ferrari. So in terms of search speed, this is pretty much like Ferrari. The only object or the only reason for people to design this data structure is just for search efficiency. It is not good at anything but search. So tell me a scenario or in which case you are going to be using a lot of search.
On Google?
On Google, yes. Cool. That's extremely cool. Yes, on Google, we're going to do a lot of searches, right? So, and then how to find the pages that includes the keywords that you're just tapping. Okay, that is done by RBTree. Okay, so basically let me say the RBTree is widely used in an area named database. Okay, so if you have a database, for example, a database of students or a database of web pages, so with the database, we mostly the people organize data into a database just mostly for search. So like Google, what Google how Google deals with so many pages, web pages. So and so in that case, because we're going to perform a lot of search, people just organize the database by using RBTree. So the underlying data structure below a database is just a RBTree. So we can get ultimate performance in search. So it's guaranteed to be fast. Okay, so this is the most advanced version and of data structures for search. and so you are going to have a little bit of touch with it in your database class or operating system class. But I'm not going to go through the details of that, and it's really difficult. And so if you want to understand it, there is a chapter in our textbook which is like 45 pages, around 40. There are around 45 pages in our textbook which introduce this data structure. If you are interested, you can just go to explore it by yourself. And I'm saying maybe 2 or 3 years ago, one of the students in my class say he's extremely interested in this one, in this data structure. So he spent a whole month just to understand it and implement that. So we had a lot of discussion, and so in the last, his data structure can work, but there is there is some bug, but it's already good enough. I think he wrote more than 1,000 lines or so for that project in Java. And so and the good thing about that experience for him is that this is the end of our term, the end of the semester for him. Okay, so just like 2 days or 3 days after the end of the end of the semester for him, so JP Morgan Chase scheduled a summer internship interview for him. Okay, so and because it's just 2 days from the end of the semester, he doesn't have too much time to prepare for that internship interview. So what he did is that so definitely the interview consists of several coding questions, and he did them okay, not too good, not too bad. But what really makes him stand out is that, so after the code interviews, they invite him to a dinner or lunch, I don't remember. And throughout that meal, he was talking with the other people about the RBTree that he implemented, what kind of difficulties he met, and his understanding of this data structure. And that really makes him stand out. So he got it. He got that internship opportunity, and I think now he's a full-time employee over there as a software engineer. So the purpose for me to introduce his experience, and after that he sent me an email, a very long email to express his gratitude, and also but what I said is that you earn it, not me. So it's his efforts who earned him the internship, not me. So what I want to say is that, okay, because all of you basically take the same course, so everyone takes data structures, everyone takes database, and as long as you can graduate, you have to take the same case. So at the time when you leave the campus, when you graduate, almost for those outside employers, all of you pretty much similar to each other. There is not much a big difference. Someone got a B from a course, someone got a B plus, someone got a or A minus. That's fine. So still, it's not much. The difference between among you is not very big. So what can really make you stand out is some experience like this. Okay, so it's going to be a big plus for you. So if you are really if you really have ambitious about your career, and then say in your sophomore year, so when you become a sophomore or senior person, then so in your senior year, so you should definitely seek to do a big project under the supervision with an advisor. You can find an advisor from our department, and let that person be your advisor, and work hard on that. And so this can make you stand out when you are hunting for your full-time jobs after graduation. So that's my suggestion. And okay, so and then so there is one more data structure that I want to introduce that is called hash table. And this data structure is really interesting. So, so is there anyone who have used this data structure in Java?
No.
No? Actually, this data structure is provided by Java in the package java.util. Under util, there's a Java already implemented. It's called hash table. So you just need to Google it to find the API of that. So let me just Google it for you. Oh, I think it's called hash map, not hash table. Yes, hash map. Yes, this is what is provided by that. Okay, so you can just go to read it by yourself. And let's come back. So let me just. The beauty of this data structure are in two ways. First, I'm just going to give you a conclusion. It supports O1 search complexity. Okay, so it's guaranteed to be O1. And so which is the most efficient search complexity that all of us can expect. And this is one interesting part. The other interesting part is that it is based on a hash function. And then do you know where is nowadays what is the most famous application of hash? Come on, you should have heard about it. Okay, so so in this year or since the pandemic starts, what is the best investment choice?
Oh, does it have to do with cryptocurrency?
Yes,
Hash?
Bitcoin.
Yeah.
Yeah, like hashing and like, okay.
Yes. Okay. So hash is it shares the same foundation, theoretical foundation, scientific foundation with Bitcoin or with blockchain. So I'm going to introduce that now. So first, what is a hash? Okay, a hash is basically a function. Let me just write it as h. It's just a function. So this function has three properties. Okay, so here let me write it as an h. H is the function, and here one thing is that you can pass it in. You can pass to this function any x. X is the input parameter. X can be anything. X can be a string, can be an integer. X can be a file, or it can be anything basically. So anything of any length. So it can be as just one number, or say an array of 1 million numbers, and its output y is going to be guaranteed to be a fixed length, random output. I'm ignore. Okay, it's going to be a fixed length output, and this output seems totally random to us. It does not make sense. So imagine this. Okay, no matter if you pass in a single number or 1 million numbers, the output length is going to be the same. So the result is going to have the same length. And usually this length is going to be really short, either 128 bits or 258 bits. Okay, so something like that. And so 1 byte is equal to, considering that 1 byte, it means 8 bits. So this means it's going to have 16 bytes, or say 32 bytes. So the output length is going to be very short. And so this is one property. And the other property, another property is that it is infeasible, computationally infeasible, for you to find x1 and xy, which are not the same, to find two different input, which come up with the same output. Okay, so you cannot find, it's very hard for us to find two inputs with with the same two different inputs with the same output for the hash function. Okay, and by computationally infeasible, it means that okay, even though you are given the most advanced computational resource, let's say the most powerful computer in this world, is going to take you at least 200 years to find such a pair, and by that time, all of us will disappear. So, so that's what we mean by computationally infeasible in our lifetime. Okay, so this is the second property, and the third property is that okay, so giving x, you can easily find y. So you just need to feed x into this function, and it will just output this. Give you the output in a very fast way. But if you know x, if you only know y, and you want to get the reversion, you want to get the inverse of inverse of this function. Basically, the inverse of this function is not. I'm just putting the inverse of this function is also computationally infeasible. Is also computationally infeasible. So meaning that giving y, if you're giving an output, you cannot find the corresponding input in your lifetime. So this is the property of the three properties of hash function. And let's say how it makes in so how do we apply it in Bitcoin? So in Bitcoin, do you know how can you earn Bitcoin? Instead of paying the cash,
mining
like 50,000 for it, mine, right? Do you know what? So how do you mine a coin?
Aren't you just trying to solve like I guess a problem over time, and then like if your computer gets it, you get the Bitcoin or something like that?
Yes. Okay. So the thing is that in the Bitcoin world, so if you want to participate in a competition or say do the mining work, then you are going to receive two input, N and C. So C is C. We call C the challenge, and we call N the nonce. Okay. So your task is to find you need to find x. You need to find x such that the addition between h and the hash of x plus n equals to c. So basically, you are going to inverse. What you are asked to do is to giving the output, giving a certain output, you need to find the corresponding input of it for the hash function, and which is computationally infeasible. Okay, this has basically the way for you to get a coin, to mine Bitcoin, is to solve a computationally infeasible problem. So then to do that, you need to have a supercomputer which consists of multiple GPUs, and then you have to be extremely lucky. So and you have to be extremely lucky and to find it. Then because the challenge is relatively easy. It's not that difficult. It's not going to take 200 years. Instead, it's going to take some time, and the time is measured in this way. The time span, the difficulty of this challenge is that okay, now at the current time is going to take around $10,000 of electricity on average. Okay. So basically, if you are lucky enough, and if you have a very powerful computer with multiple GPUs, and then if you are fortunate enough, you are able to find, you are going to just able to mine what is worth a Bitcoin value. Let's say $50K is just this X. It's just you are going to be able to find this X by paying around $10,000 of electricity bill, and then you get it, and you get like 50,000. You get a Bitcoin as your reward, and currently it is worth, I don't know, so maybe 30,000, maybe 50,000. So that is how Bitcoin works based on hash function. Okay, any question for me? Oh, 59K. Okay, so which is superb. So 3 or 4 years ago when I joined, 4 years ago, when I joined Montclair, so I bought a personal cluster with, I spent around $100,000 on a computational cluster with 4 RTX 2080 Ti GPUs. So at that time, that server cost me around $100,000, and for my research purpose, because I was running some deep learning models. I was training some deep learning models. I need that, and so this is something that I always regret. Okay, if I just bought it not for research but just for mining Bitcoins, now I could be a millionaire. I definitely would be a millionaire, but I didn't do that. So at that time, I thought, okay, it's not worthwhile to do so. But now it seems that with the government just keep printing money, and the Bitcoin price is going to keep rising, because at the time when that Japanese genius designed Bitcoin, so the number of Bitcoins is just fixed. Is constant. It's predetermined. They're just this amount of Bitcoins. So it is a very, very good tool to fight against the inflation. Oh, by the way, so do you know what is going to happen this year and also next year in terms of inflation? At 21 million Bitcoins. Okay, so I don't remember exactly how many are there. You know, in terms of, yes, hyperinflation. So expect 10% inflation, meaning that, so usually we got a figure named the CPI, consumer purchase index, which is a measure like how costly it is to have a life. Yes, okay. I got a chat message saying they reduced the hash speed by half about 3 months ago, I think. Okay, the thing is that, okay, they monitor the amount of time that you spend on all the miners spend on mining a certain coin, a Bitcoin. Like they take the average time. If the average time is too slow, they're going to increase the difficulty of the new challenges, and so that they make sure that the rate to produce new Bitcoins, for us to find new Bitcoins, is constant. So okay, so they may reduce the speed or they may increase the speed just based on the performance. It's just based on the average time that you spend on mining a certain a Bitcoin. And basically, so, but we usually only say that they reduce the so they increase the time. They increase the time or reduce the not reduce the hash speed. They increase the difficulty of the challenge, because we keep getting better and better computational power. Okay, so usually let's come back to this. Okay, let's talk about CPI. So usually the CPI rate is around 2.1% or 1.5%, etc. And so this year starting from this year and also next year, it's guaranteed that we're going to get at least 10% inflation, and this inflation is not going to. So most of the inflation is not going to heavily impact the price of milk or the price of vegetable or the price of meat. No, they're going to heavily so what is going to the price of the following things are going to increase a lot. So first, stocks, and then real estate, the houses, estate. And so okay, these are, if you hold stock or if you invest in them, then that's good news for you. But for you guys, because you're so young, I don't think you are going to have a lot of them. The bad thing is that, okay, the price in education is going to skyrocket again. So so the last time when when a developed country saw this crazy inflation rate was in 1934 or so, when in Germany, and so a couple of years later, 3 years later, or yes, 3 years later, they started World War II. So, I mean, in a developed country, I say a chat saying a message saying that in 1980s, I think in 1980s, some South American countries like Venezuela, they got this crazy inflation rate, but in a developed country, the last time we saw it was in Germany, and 3 years later, they started World War II. So that's extremely bad. So I mean, so be prepared. So probably in the next couple of weeks, I'm going to tell you a couple of strategies for you to fight against this inflation, because it's a bad thing for you. Okay, so then let's come back to hash table. So the way for us to so imagine how can we get the how can we make sure that we get O1 search complexity? How can we get O1 search complexity? So if you want to find a value k in an array, how do you get the O1 complexity, search complexity? If you know the index of that value immediately, you will be able to get the O1 complexity, correct?
Yeah, that's right.
Yes, it's like if I say, okay, I want to look for a certain person at Montclair. And so one way is that I just go to the campus and ask everyone, are you Kevin? Are you Kevin? And in the worst case, I have to ask everybody. But if there is a match which says, okay, I say, oh, if I tell you, okay, I want to find Kevin, and you just tell me. If you can tell me immediately, say, okay, Kevin is located in which building, which room, then yes, I'm going to be able to find that person in constant time, no matter how many students are there on campus. Correct?
Correct.
Yeah.
Okay. So the way for us to find the index is based on hash. So that is like this. Okay, we have an array, and so every time when we have a new value to insert into this array, let's say we have a value v1, we want to insert this array. We need to know. So we use hash to calculate the we do the hash over that, and we use the hash modular the length of the array as the index. The index of this value is going to be the hash value of it, modular the index, and then modular the length of the array. Then we're going to put it into this place. And next time, when we want to look for v1, we just follow. When we just want to look for value, we just need to take the hash over it and modular the length, and then go to that specific place and find it. That is how it is done. As long as the value exists, it must be in this place. So basically, hash table is just an array, but we are using the hash to determine the index of these values. Where are we going to place these values? Simple? So basically, we are going to use the hash to determine the value for us to put a value, and also we follow the same way to search for values. And because so next time, no matter which value do you want to search for, we just need to take the hash of it, a certain value, and modulate the length of the array. Go to that place, constant time, no matter how many elements are there in the array. This is your operation, constant time. Okay, so any question with how does hash table work? Is that clear?
Yeah, it's clear.
Yeah, no questions.
Okay, so in terms of the search speed, over here, hash is the best one. Hash is really the best one, which gives you the O1 search complexity. But some of you may ask, why in database, why not implement database in hash table rather than RBTree? Because it gives O1 search complexity, which is better than O log n. The reason is that with hash, we usually only support, there is one limitation with hash, which is that it's based on array, and we can only store small amount of data in array. Okay, because we need to store the arrays in our physical memory rather than on the disk, rather than on the hard drive. So there is a big limitation on the size of the total size of the data that we can store on a hash table. So that's why it's rarely used. I mean, so if you want to say we can take, I think we can take the hash as something like, let's do not use Ferrari for that. Let's use this one, Mercedes-Benz for RBTree, and then use let's say for RBTree, let's just give it Porsche. Okay, and then hash table is pretty much like a Ferrari, which runs extremely fast, but you cannot drive a Ferrari on New Jersey road. No. So you are going to break your tires every mile, and the car is going to fall in parts very soon. Okay, so does that make sense?
Yep.
Yeah.
Okay,
yeah.
Sure. So yes, then that's what I want to discuss so far. Okay, so for today, and so any question for me before you leave? No? Okay, so let me ask you one question. How long have we spent together? How long have we get in touch with each other? Like 6 weeks or 6 or 7 weeks, right?
Yeah, I think it's like 7 or 8.
6, 7 weeks. So we are basically a half of the semester. And so we finished the first half of the semester. And so I'm not sure how do you like this course so far, and how do you like my teaching style so far. So, but I want to know that. I desperately want to know that. So so in the second half, I can know how to do better for you. And so I'm not going to ask you, okay, so how do you like me, or how do you like my teachings? So if it's pretty much like I put a gun in front of you and saying, okay, I ask you to say good words about me. No, I'm not going to do that. So do you know there is a famous website?
Do rate my professor?
Yes, that's the Yelp for professors, right? Yelp for professors. That is called Read My Professor. Just go to that. So if you have any comment on me, no matter it's good or bad, just go to that. Just go to that website and Google my name and search my name. There's only one profile with the same name as me. So that's me. And so no matter what you want to say to me, okay, just go there to make your comment, so that I'm going to read the comments and say how to do better in the rest of the semester. And also, I think the best value for those comments are that in the future, if a student wants to take a certain class, for example, that structure, and if me and my colleagues both offer these courses, they can use it as a reference to determine say which class to go for, and for their best interest, which one fits their interest the best. So I would appreciate that if you can take up a couple of minutes and provide your feedback over there. And by the way, it's anonymous. I'm not going to know who leaves a bad comment, who leaves a good comment on me. It doesn't matter. I just want to know your honest opinions. Okay, so yes, then that's it. So then and that's it for today. So yes, have a good weekend.
Have a good weekend, Professor.
Bye.
Thank you.
Have a good weekend.
Thank you,
Thank you.
Professor.
Thank you.
Quick question. Do we have homework for hash?
Professor, you're muted. You're still muted. You are still muted.